In the late 1950s, the vast assembly lines at Filton finally fell quiet. The Bristol Hercules, a sleeve-valve radial engine that had powered Britain through its darkest hours, was systematically being pushed out of the sky. This was no fragile prototype. Bristol had cast and machined over 57 out of 400 of these complex 14-cylinder power plants. They had carried Beaufighters over the Channel and lifted Halifax bombers into the night. Yet within a few short years of peacetime, the military orders evaporated and commercial airlines rushed to replace them. For the maintenance crews of the Royal Air Force, this silence meant the loss of a perfectly balanced, gear-driven masterpiece. For the factory machinists, it meant the end of an era where British metallurgy was pushed to its absolute limit. The paradox is that the Hercules did not fail because it lacked power. It failed because it was too complex, too demanding to manufacture in a peacetime economy, and entirely defenseless against the scream of the new gas turbines. But the real story of the Bristol Hercules is not only the story of how a factory line died, it is the story of how Britain built the ultimate piston engine, just moments before the world stopped needing pistons at all. Every week, we tell the stories of British engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place, in the engineering offices of the Bristol Aeroplane Company in 1935. In the mid-1930s, the British aviation industry was quietly approaching a mechanical wall. At the Bristol Aeroplane Company in Filton, the chief engineer, Sir Roy Fedden, understood that the radial engine, a piston aircraft engine with cylinders arranged in a circle around the crankshaft, was about to reach the physical limits of its own breathing system. For decades, the internal combustion engine had relied almost exclusively on the poppet valve. A poppet valve is essentially a mushroom-shaped metal plug pushed open by a camshaft and slammed shut by heavy springs, allowing fuel in and exhaust gases out. In a standard motor car, this was perfectly adequate. But an Aero engine, an engine built for aircraft use, where power, weight, reliability, and certification matter differently from road vehicles, was a much more brutal environment. As the Air Ministry began writing specifications for a new generation of heavy bombers and fast-strike aircraft, they demanded horsepower figures that pushed piston engines into highly stressed territory. To get more power, an engine had to spin faster and burn hotter. When conventional poppet valves were forced to operate at extreme speeds, the heavy metal springs would bounce, float, or simply shatter under the stress. Furthermore, the complex rocker arms and push rods required to operate these valves meant that the cylinder heads of a radial engine had to be wide and bulky. In the air, bulk creates drag, and drag steals speed. Britain lacked a power unit that could deliver over 1,000 horsepower without tearing its own valve train apart, while remaining compact enough to slip through the air efficiently. Fedden's solution was not to build a better spring. His solution was to eliminate the conventional valve entirely. He committed the Bristol engine department to the sleeve valve engine, an engine that uses moving sleeves instead of conventional poppet valves to control gas flow. In this design, a thin, perfectly machined cylinder of metal sits between the piston and the outer cylinder wall. As the piston moves up and down, this sleeve also moves, driven by a complex internal gear train. It slides vertically while simultaneously twisting left and right. Precision-cut holes or ports in the sleeve line up perfectly with exhaust and intake ports in the cylinder block at exactly the right fraction of a second. There were no springs to break. There were no valves to bounce. The cylinder heads could be completely flat, drastically reducing the frontal area of the engine and allowing for a tight, highly aerodynamic cowling. In theory, it was a masterpiece of mechanical elegance. In reality, it was a metallurgical nightmare. The engineering required to make a piece of thin steel slide against an aluminum cylinder wall and a moving piston under extreme combustion heat, millions of times without seizing, warping, or leaking oil, was staggering. Early experiments in the Filton test sheds were disastrous. Sleeves would expand under the immense heat of combustion and instantly weld themselves to the cylinder blocks. Engines would tear themselves to pieces on the test stands. The scrap rate for these early components was astronomical. If a sleeve was machined even a fraction of a thousandth of an inch out of tolerance, the entire power unit would destroy itself within minutes. This was Force 1 in action: iron, aluminium, fuel, and manufacturing costs. The cost of developing the sleeve valve was bleeding the company. Bristol had to invent entirely new machining techniques just to cut the metal. They experimented with dozens of alloys before settling on a highly specialized austenitic steel known as KE965, which could withstand the severe thermal shock. They had to perfect a process of centrifugally casting the metal to ensure it had no microscopic flaws. The grinding machines on the factory floor had to be recalibrated to tolerances that most British manufacturing industries had never seen. Even the lubrication system had to be entirely rethought, as the sliding sleeves required a precise film of oil to prevent friction, but pumping too much oil would foul the spark plugs and create massive exhaust smoke. Despite the internal doubts and the immense financial strain, Filton refused to abandon the architecture. By 1936, the persistence began to yield physical results. Bristol successfully ran single-row sleeve valve engines, such as the Perseus, proving that the geometry could work in sustained operation. But the Air Ministry needed far more power than a single row of cylinders could provide. They needed a heavy-duty platform. The answer came in the form of the Bristol Hercules. First run on a test stand in 1936, the Hercules was a two-row, 14-cylinder radial engine with a massive displacement, the total volume swept by the pistons inside the cylinders, of 2,260 cubic inches, or roughly 38.7 liters. With a bore of 5.75 inches and a stroke of 6.5 inches, it was a dense, heavy block of tightly packed engineering. Initially targeting an output of 1,290 horsepower, it represented a massive leap in capability. Because it had no conventional valves clattering away in the cylinder heads, it ran with an eerie sewing machine smoothness. The traditional mechanical clatter of a large aircraft engine was entirely absent, replaced by a deep, continuous, rushing hum. Early reception from the British aviation establishment was cautiously optimistic, but heavily skeptical of the manufacturing complexity. The trade press noted its exceptionally clean lines and low drag profile, but engineers outside of Filton openly wondered if such a machine could ever be built in volume. It was one thing for a team of master craftsmen to hand-build a perfect sleeve valve engine in a sterile laboratory environment. It was quite another to mass-produce it. Mechanics in early service networks looked at the complex sleeve drive gears and wondered how they would ever maintain such a Swiss watch mechanism in the field. Yet by 1939, as the shadow of conflict stretched across Europe, the engine achieved its first major British breakthrough. The Hercules began to find its way into the airframes of early heavy aircraft. It promised high volumetric efficiency, lower fuel consumption, and the absolute elimination of valve failure, a critical factor when flying long missions over hostile water. The block was solid. The tolerances were locked in. The test stands had proven that the sleeve valve radial was no longer an impossible dream, but a working, breathing reality. The prototype proved that the sleeve valve could survive the test stand. But Britain was about to ask Bristol to prove it could work in the sky by the thousands in the darkest years of the century. By 1939, as Britain prepared for a war of industrial attrition, the Bristol Aeroplane Company was ordered to turn a delicate metallurgical miracle into a mass-produced weapon. The Air Ministry did not just want a few hundred of these sleeve valve radials, they demanded thousands. The Hercules was about to transition from the sterile environment of the Filton testing sheds to the brutal, freezing, mud-soaked reality of frontline bomber command airfields. The breakthrough of the Hercules was not merely that it worked without destroying itself, but what its unique architecture allowed British aircraft designers to achieve. At the time, Britain's aviation strategy relied heavily on moving massive payloads across long distances, often at night. This required heavy four-engine bombers like the short Stirling and the Handley Page Halifax. These aircraft were vast, heavy, and required immense low-end pulling power to lift their bomb loads off short, grass runways. The Hercules provided exactly that. Rated at over 1,300 horsepower in its early production iterations, horsepower being a measurement of how quickly an engine can do work. The 14-cylinder radial delivered a sheer mechanical grunt that few contemporary power units could match. But the true genius of the sleeve valve design became apparent not on a heavy bomber, but on a twin-engine strike fighter, the Bristol Beaufighter. To understand why the Hercules made the Beaufighter so lethal, one must look at the front of the aircraft. A traditional radial engine, with its overhead valves, rocker arms, and push rods protruding from the top of every cylinder, is aerodynamically messy. It requires a large, bulbous metal cowling to cover the mechanical clutter, creating immense drag. The Hercules, however, had perfectly flat cylinder heads. Because the sliding sleeves were controlled by a gear train hidden deep inside the block, the main engine structure that holds the cylinders and internal parts, there was no valve train sitting on top of the combustion chambers. This allowed Bristol to wrap the engine in a remarkably tight, streamlined cowling. In the air, a smaller frontal area translates directly into speed. Powered by two Hercules engines, the heavily armed Beaufighter could reach nearly 330 miles per hour, making it a terrifyingly fast night fighter and maritime strike aircraft. Furthermore, the Hercules was air-cooled, relying entirely on the forward motion of the aircraft to force cold air over the metal cooling fins machined into the cylinders. This stood in stark contrast to its most famous British rival, the Rolls-Royce Merlin. The Merlin was a liquid-cooled V12, a 12-cylinder engine arranged in two banks in a V-shape. While the Merlin was brilliant and aerodynamically sleek for single-engine interceptors like the Spitfire, it relied on a vulnerable radiator and a complex network of plumbing to keep it from overheating. In the low-level maritime strike roles assigned to the Beaufighter, aircraft were frequently subjected to intense, close-range anti-aircraft fire from enemy shipping. If a single stray bullet pierced a Merlin's cooling system, the engine would drain its coolant and seize solid within minutes. If a bullet passed through a cooling fin on a Hercules, the engine simply kept running. This mechanical survivability earned the Hercules the absolute trust of coastal command pilots flying long, dangerous sorties over the North Sea. But an Aero engine only survives if the service network on the ground can keep it running. In the context of 1940s Britain, that service network consisted of thousands of Royal Air Force fitters and mechanics, often working outdoors in the freezing rain of Yorkshire or the blinding dust of North Africa. Here, the sleeve valve presented a massive operational advantage. With a conventional poppet valve engine, routine maintenance was a tedious, labor-intensive nightmare. Mechanics had to constantly remove rocker covers to manually adjust the clearances of dozens of valves, a job that required absolute precision with a feeler gauge, often executed with freezing, oil-slicked fingers. If the clearances were wrong, the engine ran poorly or burned its valves outright. The Hercules eliminated this entirely. There were no tappets to adjust. There were no springs to check for tension. From the perspective of a frontline mechanic, the top end of the engine was completely maintenance-free. You changed the spark plugs, you checked the oil flow, and you left the internals alone. When the engine eventually reached the end of its operational life, squadrons did not attempt a complex field overhaul, a major service process where an engine is taken apart, inspected, and rebuilt to operating standards. Instead, mechanics simply unbolted the entire power unit from the aircraft's firewall, fitted a fresh one directly from the supply crate, and sent the tired block back to a specialist machine shop in the Midlands. The Hercules also solved a critical fuel problem. The fuel system drew air through a massive carburetor, a device that mixes fuel and air before the mixture enters the engine, before being compressed by the supercharger. A supercharger is a mechanically driven device that forces more air into the engine, allowing it to maintain power at high altitudes where the atmosphere is thin. Because the moving sleeves opened up massive intake ports very quickly, and without the obstruction of a hot exhaust valve sitting in the way, the engine could swallow a massive volume of fuel and air with incredible volumetric efficiency. This allowed the Hercules to run on exceptionally lean fuel mixtures during long cruising flights, offering fuel economy that traditional radials could not match. For a Halifax bomber crew returning from the Ruhr Valley, or a transport pilot crossing the Mediterranean, that efficiency was the difference between reaching a British runway and ditching in the sea. Unlike the sharp, aggressive crackle of a Merlin, the Hercules produced a deep, resonant, rushing thrum. It was a sound that British air crews and mechanics learned to trust implicitly. Yet the very design that made the Hercules a masterpiece on the airfield made it a terrifying logistical challenge at home. The demand for the engine was completely outstripping the capacity of the original Filton workforce. To produce the sleeves, Bristol required specialized centrifugal castings. To machine them, they needed grinding tools that did not exist in standard British manufacturing catalogs. Bristol had solved the engineering problem. Now they had to build an industrial empire to feed a war that consumed engines faster than the foundries could cast them. By 1942, the Bristol Hercules was no longer just an experimental engine. It was a sprawling industrial system that consumed entire British towns. The original Filton works, massive as it was, could not cast, machine, and assemble the sheer volume of metal required by the Air Ministry. The demand forced the creation of a vast shadow factory network, covert manufacturing plants dispersed across the country to protect them from aerial bombardment. Deep in the Midlands and up in Accrington, thousands of factory workers, many of them women who had never touched a micrometer before the war, were trained to grind austenitic steel sleeves to tolerances measured in the tenths of a thousandth of an inch. This was the peak of British piston manufacturing. At its height, the Hercules ecosystem produced an astonishing 50 400 complete engines. Each one represented 14 cylinders of perfectly timed, sleeve-valved power, requiring hundreds of bespoke gears, precise centrifugal castings, and a flawless lubrication system. On the frontline airfields of Bomber Command, the Hercules became the mechanical spine of the heavy offensive. While the Rolls-Royce Merlin captured the public imagination in the sleek nose of the single-engine Spitfire, it was the deep, droning thrum of the Bristol Radial that hauled the heavy bombers into the freezing night sky. The Hercules was bolted to the wings of the short Stirling, the Vickers Wellington, and the Handley Page Halifax. Even the legendary Aero Lancaster, a machine universally associated with the Merlin, was fitted with the Hercules in its MK2 variant to ensure production would not halt if Rolls-Royce factories were compromised. In these vast four-engine applications, the Hercules was trusted for its sheer, unrelenting durability. An Aero engine is not just a machine that generates thrust. In the context of a 1944 bombing raid, it was a lifeline. If a Halifax took heavy anti-aircraft fire over Germany, the Hercules was famously capable of swallowing battle damage that would have instantly destroyed a liquid-cooled engine. It could lose oil pressure, shed cooling fins, and still drag a crippled bomber back across the North Sea to a fog-bound runway in Yorkshire. But the true glory of the Hercules was that its brilliance did not end when the war did. As peace settled over Europe, Britain faced a new kind of aviation problem. The country needed to rebuild its global transport links, shift cargo, and move troops across a fractured empire. The military surplus was vast, and the Hercules was immediately drafted into the civilian and transport sectors. The engine transitioned seamlessly from wartime bombers to peacetime haulers. It powered the Handley Page Hastings, the workhorse of the Royal Air Force's transport fleet, which famously flew through freezing conditions to deliver vital supplies during the Berlin airlift in 1948. It lifted the Vickers Valletta military transport, and it became the beating heart of the Bristol Freighter, a blunt, heavy-lifting cargo aircraft that carried everything from fresh produce to luxury cars across the English Channel. In the late 1940s, the Hercules was continually refined, with later marks pushing well past 2,000 horsepower. It was a masterpiece of mechanical maturity. The early metallurgical nightmares of the 1930s had been entirely solved. The sleeves no longer warped. The oil consumption was controlled. The complex internal gear trains ran with absolute, predictable reliability. The British aviation industry had achieved the impossible. They had made the most complex valve train in the world entirely routine. But that very routine was about to mask a fatal economic vulnerability. At the peak of its glory in the late 1940s and early 1950s, the Bristol Hercules was not just a piece of machinery, it was the foundation of a sprawling British service network. Across Royal Air Force bases and commercial airfields, from the tarmac of Filton to the dusty runways of the far-flung Commonwealth, an entire generation of fitters and mechanics had been trained to understand the sleeve valve architecture. Surviving oil-stained service manuals from this era reveal the sheer scale of this ecosystem. A mechanic did not merely fix a Hercules. They operated within a vast, highly coordinated supply chain of prepackaged spares, regional overhaul depots, in strict maintenance schedules. If a commercial Bristol freighter or a military Vickers Valletta required a major overhaul, the operator rarely attempted to tear the complex block apart in a drafty hangar. Instead, they unbolted the entire power unit, fitted a fresh replacement, and sent the tired engine back to specialist machine shops. There, in well-lit, heavily equipped British workshops, the intricate gear trains were stripped, inspected, and rebuilt to original factory tolerances. In a Britain where an engine could decide whether an aircraft lifted from a grass airfield, a heavy transport made its delivery across a fractured empire, or a commercial flight survived a crossing in freezing weather, power was not an abstraction. It was metal, fuel, labor, heat, sound, repair, risk, and absolute trust. And the Hercules earned that trust through its signature acoustic footprint. A conventional radial engine announces itself with the frantic, metallic clatter of valves, push rods, and springs, a mechanical noise that hints at the violent forces barely contained beneath the rocker covers. The Hercules, completely devoid of an overhead valve train, possessed a distinct, rushing mechanical drone. For the crews flying the Handley Page Halifax on long-haul transport routes, or the pilots wrestling a heavy cargo aircraft over the channel, that smooth, uninterrupted thrum was the ultimate comfort. It meant that the internal sleeves were sweeping in perfect harmony, the austenitic steel was holding its shape under intense heat, and the engine was breathing exactly as it had been designed to. By the early 1950s, the engine had achieved absolute mechanical maturity. The terrifying scrap rates and metallurgical failures of the 1930s were completely forgotten. It was powerful, highly reliable, and deeply embedded in both military transport and civilian freight fleets. The Bristol Engine Department had successfully industrialized the most complex valve train in the world. It seemed entirely invincible. The foundries were pouring metal. The specialist grinding machines were perfectly calibrated. The mechanics understood the exact rhythm of the engine. But this vast enclosed ecosystem existed entirely because the desperate economics of a world war had allowed Britain to ignore the immense cost of such complexity. The Hercules had won its war and proved its design, but the same engineering that made it brilliant was about to run out of time. The first crack in the Bristol Hercules empire did not sound like the roar of a jet turbine. It sounded like the quiet, unforgiving mathematics of a peacetime balance sheet. When the Second World War ended in 1945, the vast military contracts that had fueled the expansion of the Filton works evaporated almost overnight. The British government was no longer writing blank checks for heavy bombers. Suddenly, the Bristol Aeroplane Company had to transition from a state-funded arsenal back into a commercial enterprise, selling engines to civilian airlines and a heavily downsized Royal Air Force. This was the brutal reality of Force One: iron, aluminium, fuel and manufacturing costs. During the conflict, the extreme expense of manufacturing a sleeve valve radial was justified by its aerodynamic advantages and its ability to survive combat damage. In peacetime, commercial operators like British European Airways, flying the new Vickers Viking airliners, did not care about surviving anti-aircraft fire. They cared about the cost per seat mile, and it was here that the sheer mechanical complexity of the Hercules began to trap it. To understand why the engine became an economic burden, one must look at the factory floor. A conventional poppet valve engine, for all its clattering push rods and springs, is relatively cheap to manufacture. The valves are simple metal stamps. The springs are standard industrial components. If a valve burns out, a mechanic can pull the cylinder head in a hangar and replace it in an afternoon. The Hercules offered no such simplicity. Every single one of its 14 cylinders required a bespoke, centrifugally cast sleeve made from highly specialized austenitic steel. These sleeves had to be machined and ground to tolerances so tight that even a microscopic flaw would cause them to bind against the aluminum block. The internal drive mechanism, a complex array of crankshaft-driven gears, lay shafts, and ball joints required to make the sleeves twist and slide simultaneously, was a masterpiece of precision engineering. But precision is expensive. The specialized grinding machines at Filton required constant recalibration, and the highly skilled labor needed to assemble the gear trains demanded premium wages. In the late 1940s, independent British freight operators and charter airlines were flooding the market. Many of them bypassed the Hercules altogether, choosing instead to buy war-surplus American aircraft like the Douglas Dakota, powered by conventional Pratt & Whitney radials. Those American engines were cruder, louder, and aerodynamically messier than the Bristol masterpiece, but their spare parts were scattered across the globe for pennies, and any mechanic with a spanner could adjust their tappets. The Hercules, by contrast, remained a premium, highly integrated system. When a Bristol freighter or a Handley Page Hermes required an engine overhaul, the operator could not simply fix it on the tarmac. The entire power unit had to be crated up and sent back to a specialist Bristol-approved machine shop. There, the complex block had to be split, the internal sleeve drive gears rigorously inspected for microfractures, and the sleeves checked for perfectly even wear. If the tolerances had drifted, the parts could not be adjusted. They had to be entirely replaced with expensive factory-new components. For a few years, the sheer reliability of the Hercules kept the orders flowing. It was a known quantity, and its smooth, rushing sound was deeply trusted by British crews crossing the Channel or flying the arduous routes to Africa. But behind the doors of Bristol's own engineering department, the writing was already on the wall. Even before the war had ended, the British government's Brabazon Committee had convened to plan the future of the nation's civil aviation. Their conclusion was absolute. The future of heavy aircraft did not lie with the piston engine. It lay with the gas turbine. At Filton, a quiet but devastating internal shift began. The brilliant minds of the Bristol engine department, the metallurgists who had solved the sleeve valve nightmare, the draftsmen who had perfected the gear trains, were slowly reassigned. The company's research and development budget was being funneled away from the Hercules and poured into a new, radically different project, the Bristol Proteus. The Proteus was a turboprop, a turbine engine that drives a propeller. Unlike the Hercules, which required 14 massive pistons to violently change direction thousands of times a minute, a turboprop relied on the smooth, continuous rotation of turbine blades spinning in a high-speed flow of burning gas. It was lighter, it promised vastly more horsepower, and crucially, once the initial development costs were absorbed, a turbine was fundamentally simpler to maintain, with fewer moving parts rubbing against each other. The mechanics on the factory floor assembling the Hercules could see the transition happening across the campus. The piston engine lines were still running, but they were no longer the vanguard of British engineering. They were legacy equipment, building out the final iterations of a technology that had mathematically reached its zenith. There was simply no more power to be safely extracted from the 38.7-liter block without making the engine completely unviable for commercial use. The Hercules was running perfectly. The sleeves were sliding exactly as Sir Roy Fedden had envisioned a decade earlier. The aluminium castings were flawless, but the block was ready. Britain still had to decide what kind of power it wanted. The fatal blow to the Bristol Hercules was not delivered by a foreign competitor, but by the relentless momentum of British engineering itself. In 1953, British European Airways introduced the Vickers Viscount into scheduled service. It was a sleek, modern airliner, but its true significance lay under the cowlings. It was powered by 4 Rolls-Royce Dart engines. The Dart was a turboprop, and its arrival completely rewrote the economic and mechanical rules of aviation. To understand why the turboprop destroyed the sleeve valve radial, one must look at the physical violence occurring inside the metal. Even in its most refined, perfectly balanced form, the Hercules relied on 14 heavy pistons, constantly starting, stopping, and reversing direction thousands of times every minute. That reciprocating mass created vibration, heat, and inevitable wear. A turboprop, by contrast, operates on continuous rotation. It draws air in, compresses it, burns it, and spins a turbine that drives a propeller through a reduction gearbox. Once the initial development hurdles were cleared, the turbine proved to be fundamentally smoother and vastly more reliable over long periods. In the regional overhaul depots and airline maintenance hangars, this difference translated directly into money. The time between overhauls, the strict regulatory interval defining how many hours an engine can fly before it must be entirely stripped down and rebuilt to operating standards, began to stretch significantly in favor of the turbine. A Rolls-Royce Dart could stay bolted to the wing of an aircraft far longer than a highly stressed piston radial. When a turboprop finally did require servicing, there were no complex, centrifugally cast sleeves to measure for microwear, and no intricate gear trains to meticulously reassemble. Bristol's own engine department understood this perfectly. The company was actively cannibalizing its own piston heritage to fund the future. The massive engineering resources at Filton were poured into the Bristol Proteus, a large turboprop designed to power the new Bristol Britannia airliner. The investment capital required to keep the Hercules relevant, to perhaps develop a direct fuel injection system or squeeze out another 100 horsepower, completely dried up. The piston engine had reached the absolute ceiling of its thermodynamic and commercial potential. As the 1950s wore on, the vast ecosystem that had supported the Hercules began to fragment. The Royal Air Force systematically retired its piston engine transport fleets, moving to jet transports and turboprops. The Handley Page Hastings and the Vickers Valletta were gradually pushed out of frontline service, relegated to secondary roles or sent to the scrapyard. For the civilian operators flying the blunt-nosed Bristol freighter, the changing market was a slow, suffocating trap. Many independent British cargo airlines had built their businesses around the Hercules because wartime surplus parts had initially made it cheap to run. But as those military stockpiles depleted, operators were forced to buy replacement sleeves and gears directly from the factory. The sheer manufacturing cost of the KE1965 austenitic steel sleeves, machined to those exacting tolerances, became ruinous for a low-margin freight business. When a commercial Hercules reached the end of its life, it was increasingly replaced not with a rebuilt engine, but with a completely different aircraft. Back at the Filton Works, the physical landscape of the factory was transforming. The piston engine assembly lines, once the deafening, frantic heart of the British war effort, began to shrink. The specialized grinding machines that had been the absolute pride of British metallurgy in 1944 were quietly unbolted from the concrete floors and scrapped. The generation of highly skilled machinists and fitters who knew exactly how to seat a sleeve valve without binding it were either reassigned to the turbine division or quietly retired. The institutional knowledge of how to build the most complex valve train in the world was evaporating. By the time production finally ceased in the late 1950s, the world that had desperately needed the Hercules was entirely gone. The engine had not failed. It had simply been overtaken by an industry that no longer wanted to pay the price of mechanical perfection when a simpler, more powerful alternative existed. The engine still ran, the sleeves still moved, the orders stopped coming, the parts grew expensive, the mechanics retired, the sound faded, the factory still stood, but the sky above them belonged to a different kind of fire. The Bristol Engine Department did not survive the transition as an independent empire. In 1956, as the piston lines finally went cold, the division was spun off as Bristol Aero Engines. Just 3 years later, the relentless pressure of corporate consolidation forced a merger with Armstrong Siddeley to form Bristol Siddeley. By 1966, even that combined entity was swallowed whole by Rolls-Royce. The Bristol badge, which had once defined the pinnacle of the British radial engine, was entirely erased from the corporate registry. The vast Filton Works pivoted completely to turbines, aerospace components, and eventually the supersonic dream of Concord. The shadow factories in Accrington and the Midlands machine shops that had ground the steel sleeves by the tens of thousands moved on to other industries, or slowly closed their doors forever. But the Hercules itself did not vanish cleanly. Today, it survives in the quiet spaces of British industrial memory. If you walk through the hangars of the Imperial War Museum at Duxford, the Royal Air Force Museum at Hendon, or stand beneath the restored aircraft at Aerospace Bristol, you will find them. They sit in preserved Beaufighters, heavy bombers, and static museum cases. Massive blocks of aluminium and steel, frozen in time. This survival is not merely a matter of wartime nostalgia. A Bristol Hercules mounted on an engine stand is a physical argument. It is the ultimate, undeniable proof of a specific moment in British history when the country's manufacturing sector pushed the physical limits of metal cutting. It matters because it represents the absolute zenith of mechanical problem solving before the electronic age. Today, if a power unit needs to be more efficient, engineers rewrite the software-controlled powertrain. In 1939, when Sir Roy Fedden needed to eliminate valve bounce and reduce aerodynamic drag, he had to force the entire British metallurgical industry to invent entirely new ways to cast and grind austenitic steel. The Hercules is a monument to a time when physical limits were overcome not by code, but by skilled labor, extreme tolerances, and raw, deafening physical testing. When production finally ceased, it was not just metal that was retired. An entire generation of British mechanics and fitters, men and women who could assemble a sleeve-drive gear train by touch, who knew exactly how much oil a Hercules needed to stop smoking on startup, found their hard-won skills entirely redundant. The transition to the turbine era was clean for the balance sheets, but it severed a profound physical connection between the worker and the machine. The sheer tactile understanding of how to make a sleeve valve breathe could not be transferred to the sterile, high-pitched world of jet engines. Today, the knowledge of how to make this complex valve train work has largely retreated into the shadows of British preservation culture. In specialist aviation trusts and historical restoration workshops, a small, dedicated community of mechanics still pores over oil-stained service manuals. These catalogs, once printed by the tens of thousands for Royal Air Force fitters, commercial airlines, and regional overhaul depots, are now treasured texts. They hold the lost mathematics of the sleeve-drive gear trains. To restore a Hercules to running condition today is a terrifying logistical challenge. If a conventional poppet valve engine breaks a spring, a modern machine shop can easily wind a new one. But if a Hercules scores one of its 14 perfectly matched steel sleeves or fractures a complex lay shaft, there is no factory parts counter left to call. The components must be reverse engineered from scratch at immense cost, proving just how much industrial infrastructure was once required to keep these engines turning. There is a strange, often overlooked footnote to the sleeve valve story. While the gas turbine violently eradicated the Hercules from the sky, the underlying engineering brilliance of the Bristol engine department did not entirely die with it. The absolute mastery of high-temperature metallurgy and centrifugal casting that Bristol perfected, the very techniques invented to make the KE 965 steel sleeves survive extreme combustion heat without warping, was exactly the foundational knowledge required to build the first generation of reliable turbine blades. The piston engine had unwittingly funded the metallurgical research for its own executioner. The Bristol Hercules was not a failure. It was the most perfect, mechanically complex answer to an engineering question that the aviation world simply stopped asking. It was a triumph of the British machine shop, built for a world that measured progress in the reliable, rushing thrum of 14 cylinders crossing the channel in the dark. When the market shifted toward the brutal simplicity, continuous rotation, and immense thrust of the turboprop, it was not that the Hercules had broken down. It was simply that the global industry around it no longer wanted to pay the price of mechanical perfection. Somewhere in a British aviation museum, a Bristol Hercules still sits silently on an engine stand, its cooling fins dulled by time and dust, its badge still bolted to the block, forever hiding the perfect, sliding steel sleeves that once taught a nation what power sounded like. See you in the next one.